All right. Okay, good morning. Good night. Yeah, depending on where you are. So dear colleagues, students, and guests, welcome to the Faculty of Science Distinguished Lecture Series. My name is Shuang Zhang. I'm an Associate Dean of Science in China and Global. So today we are very happy to have Professor William McKinnon from the Washington University in St. Louis to give us a talk entitled Europa, the Ocean Moon, and NASA's plan to explore it. In this talk, Professor McKinnon will outline facets of Europa's geology and history, as well as NASA's plans to explore Europa and investigate its habitability. So it's my great pleasure to introduce our speaker, Professor William McKinnon, today. Professor McKinnon is a member of the Department of Earth and Planetary Sciences at Washington University in St. Louis, where he's also a member of the McDonald Center for the Space Sciences. Starting with a Voyager mission to the outer planets, Professor McKinnon, his students and collaborators have devoted themselves to studying icy satellites and the Kuiper Belt worlds, such as Pluto and impact craters everywhere. Currently, he's a co-investigator on NASA's New Horizons mission to Pluto and the Kuiper Belt, ESA's Jupiter Icy Moons Explorer, and serves on multiple teams for NASA's Europa Clipper. Without further ado, I will now pass the floor to Professor McKinnon. And yeah, welcome.
Thank you for the very gracious invitation. I'm going to share my screen to start off. And oops, that's the wrong one. Back up and show. Okay, thank you very much. I've had the great pleasure of visiting the mainland a couple of times, you know, on the North Beijing, but I've never been to Hong Kong, and maybe someday, hopefully when travel becomes more normal for all of us. Today, though, I want to tell you just about one of the most fascinating places in the solar system. I realize not everybody here is an astronomer or a geologist, so I'll try to explain things as we go along. But the important thing is that this is the frontier of exploration. Right now, Europa is a moon of Jupiter, and we believe it has an ocean, and I'm going to tell you why we think it has an ocean. And it is actually the focus of an upcoming major, or what we call flagship mission, being built today by NASA, called the Europa Clipper. It's also going to be a target for an upcoming European mission called JUICE, the Jupiter Icy Moons Explorer, but I'll say a little bit about that, but that'll be a little bit later. So let's get going. Let's start moving. So Europa is that white ornament hanging in space in front of Jupiter, as seen many years ago now, over 40 years ago by the US spacecraft Voyager 2, and it passed by Jupiter. And it's, you can see the great red spot, the famous great red spot. Europa is white. Why is it white? It's because it's covered in water ice. So it's already a kind of special world. It's one of the brightest and most reflective icy worlds of the outer solar system. There are many, but many of them are dirty, but not Europa, and that's because its geology keeps it refreshed. Now, it's not alone in the Jovian system. Here you actually see another more recent, it's a process version of, again, a Voyager 2 image. You get that telescopic effect, and you can see some details. If you can see my cursor on the surface of Europa, that's not Europa's shadow. That's the shadow of another discovered, at least from the Western point of view, by Galilei. I'm being told my connection is unstable. I will try to speak a little more slowly just in case. He, of course, was able to build a telescope in the year 1610, pointed at things in the sky, and amongst the things he saw were the 4 moons of Jupiter all lined up. But they moved hour by hour and day by day, but never left Jupiter's side. And we know now that they are a miniature planetary system. You see up here in the upper left corner, there are 4 moons: Io, Europa, Ganymede, and Callisto. And as Galileo said, 4 stars that wander around Jupiter, as does the moon around the Earth. Part of the mountain of evidence that was being gathered by him to basically prove that the Copernican view, in which the Earth was a planet that went around the sun with other planets and not the sun going around the Earth, was actually a truer version of reality. We now know that the 4 Galilean moons are, in a sense, worlds in their own right. They are a miniature planetary system. Europa is actually the smallest, but not the least of amongst all of these bodies. I really won't have any time to talk about the others. They all are orbit in the same plane. They're just like a little planetary system. They're all close into their primary, which is the planet Jupiter. And in fact, the first 3, Io, Europa, and Ganymede, are in an orbital resonance in which their orbital periods are in whole number ratio. And I'll come back to that much later. This is actually an interesting characteristic that we see out in space around in exoplanet systems. You know, there are thousands of known exoplanets, and there are several systems where there is a closely spaced group of smallish planets close to their host stars. So this is, in a way, revived astronomical interest in the origin of such a system. And it's one of the most fascinating things about Jupiter itself and its planetary system. It's not really duplicated elsewhere in our solar system, but it's out there among the stars. You can find perhaps other analogs. For this talk, though, I really am going to focus on this bright, shiny object we call Europa. It is a bright, shiny object, and it's you see on the left there is a kind of natural color version. I say it's icy because it looks like ice, but also we have infrared spectra. This has been known now for decades, and of course, spacecraft have flown by Europa and taken close-up spectra, so we know the identification that the surface is dominated overwhelmingly by water ice. But the interesting thing about water ice is it doesn't have color. Well, okay, if you have a massive amount of clear ice, it can actually look blue. But Europa's not blue. You see yellow and brown. And so there's something else there. There's something that's contaminating the ice on Europa. And this is one of the most fascinating aspects about it. The image on the right is simply an enhanced color version of the very same image. This one actually comes from the Galileo mission, which was the successor mission to the Voyagers, which were flybys. Galileo was launched and operated in the 1990s in orbit around Jupiter and made multiple passes around all of the satellites, but many passes by Europa. So most of what we know about Europa comes from the 1990s. That mission ended, and so we have only slowly began to gather up data or reanalyze old data as time has passed in the past 25 or more years. Let me just say a little bit about, to set the stage, Europa is a world, okay? It has a geological history. By passing by it, we can measure its gravitational field, so we know what its mass is. This gives us a density that is about 3 grams per cubic centimeter. So it's like ordinary rock, but the details of the gravity also, we get what's called a degree 2 gravity field, or at least part of that field. And if we interpret that through what's called the hydrostatic interpretation, we can actually infer at the very bottom number there, a moment of inertia, where a uniform sphere has a moment of inertia of 2/5. That's a classical result. But Europa's moment of inertia is less than 0.4, so we know it's centrally condensed. And so if we think of it as a world like the Earth, we can infer a structure based on general geochemical principles, that there might be an iron core surrounded by a rock mantle, and then an ice-rich outer layer. Now this cartoon you see is fits the bill, fits the data, but it is designed, it shows an ice layer floating on a thick ocean of water. The gravity field of Europa doesn't actually discriminate that well between ice and water. It discriminates between things that are very different in density, like water and rock or metal and rock. So where does this idea about Europa being an ocean moon come from? Well, it comes from someplace unexpected. The Galileo experimenters didn't know this. Oh, here's something I just forgot to say. This is a caveat. Everything I say today is provisional and is our best estimate so far. And this is just one technical slide. And the point of this slide is that someone went back in very recently, this is a 2021 paper, and reanalyzed the Doppler acceleration of the Galileo spacecraft by Europa. And you see three gray bars. And that solution to Europa's structure that I showed you in that cartoon before is that middle gray bar. And other people have different solutions, which have different gravity coefficients and therefore different moments of inertia. You can see those numbers at the top. And they don't look very different maybe by eye, but it really plays out in how thick you think that water or / ice layer might be. It could be 180 kilometers thick, or it could actually only be 120 kilometers thick. So this is the level of uncertainty that we have to carry forward with a lot of things we know about Europa. But back to my story. And my story is, how did we figure out that Europa has an ocean? Well, this is a very interesting trick. And as I said, it was not guessed at beforehand. Jupiter, the biggest planet in the solar system, has an enormously powerful magnetic field. It's generated by the convection of liquid metallic hydrogen in its interior. It is basically a giant dipole field, like the Earth's magnetic field, but more powerful, spreads out into space, and it's asymmetric. It's tilted with respect to Jupiter. Jupiter spins every 10 hours, and so its magnetic field whips by Europa basically every 10 hours, and it oscillates. And the oscillation of this field wouldn't bother Europa if it were a rock body, but it doesn't behave like a rock body. It interacts with the magnetic field, as you see in this animation, and distorts it. It distorts it as if it were a conducting sphere. Not a perfect conductor, not a giant metal ball, but a conducting sphere nonetheless. And you can analyze the magnetic field as you fly by Europa and its variation. And you can determine, or you can at least put limits on what the conductivity is of Europa. And it's much more conductive than water, ordinary water, or ice, or rock, or anything like that. It's not as conductive as metal, but it has the conductivity, if you like, of saline water, of something like seawater on the Earth. Now, of course, we can say more. So this is the technical detail. You fly by Europa, and each one of these four panels is magnetometer data, magnetic field data, both the total field at the bottom and different variations in space, X, Y, and Z. And these are two different flybys, as they're called. And the data is the red squiggles, and then the model, and the most sensitive part of the model is the top one. And if you don't have an induced response, a conductive response by Europa, you get this blue dashed line, which is not a good fit. You have to have some conductivity. And it turns out you can't really limit the upper level of the conductivity, but you can set a lower level. And it also depends on how thick that ocean is. And like I just said, we don't know. But the product of the conductivity and the ocean thickness works out to be a number of 50 Siemens per meter times kilometers. So as an example, if the ocean were 100 kilometers thick, that would mean that the conductivity would have to be at least 0.5 Siemens per meter. And then you can compare that to, an ocean, a presumed composition. And that kind of number infers that the ocean on Europa is at least what we call in English brackish. Some people don't know what that word is. It's saline, but not as salty as the Earth's ocean, or places like the Dead Sea or the Great Salt Lake in the United States. Let me just show you a graph that gives you the measured conductivity as a function of salt concentration on the bottom there on the x-axis. And that purple-blue bar is the average salt concentration of the Earth's oceans, which is about 35 grams per kilogram of water. It's quite salty. And that 0.5 Siemens per meter that I said is a lower bound, here's 0.2, 0.3, 0.4, 0.5. So if you go to sea salt, it would be over here. So It's not necessarily as salty as the Earth's ocean. It might be, but it's not necessarily so. And that actually makes sense, because if you think about the Earth has this, the ocean looks enormous, but compared to the body of the Earth, the actual amount of water on the Earth is quite limited. Whereas Europa has, in a comparative sense, much more water compared to its rock interior. So things for a sort of similar compositions, you're just going to get, it's going to be more diluted. Now this could have all sorts of interesting effects, which I can't get into right now, but that's where we're at. I have to say, though, we don't know what the ocean on Europa is made of, whether it is like the Earth's ocean. This is this one curve of conductivity versus salt concentration is for sea salt, and then there's data for something else, magnesium sulfate. There are many people who think that this is actually the major component of the salts in the European ocean. I actually don't think so, but that's a technical issue, and we don't have to get into that right away. So let's talk about Europa itself. Again, here it is. I've sort of enhanced what you can see, and you see patches and you see lines. And so we call, we're as geologists, we like to name things, so we call lines lineaments. That just means line in Latin. It's not very sophisticated. But when you see these sort of linear or arcuate structures, you jump to the conclusion, which almost is always right, that these have to do with faults or fractures in a brittle medium. Whereas the patchy stuff can be something else. And when I show you pictures of that, you'll know why we call a lot of this stuff chaos. That's an actual geologic term. And there are the occasional impact craters. But when you look at Europa, it's not a cratered body like the moon. It's much more geologically active. Here's a young crater, this bright thing, the crater is called Puel, and there's an array pattern. This is a crater made in ice. So it's very bright ejecta, but there are not that many craters on Europa. It's a very young surface geologically, almost certainly on average on the order of 50 million years old, which is quite young compared for the whole age of the solar system, which is 4.5 billion years. I'll just point out here that here's this black splotch, and there's a black sort of splotch up here. These are the two biggest impact craters on Europa, and they're not terribly prominent in this picture. Lineaments, chaos, and craters. Well, let's talk about lineaments and chaos. Well, actually, here's a blow up of a little tiny piece of Europa, and you can see some of those lineaments there. Those lines are literally linear structures, the ridges and troughs in the ground. But before I talk about them, I want to talk about the stuff below the X. People were very interested in this cross-cutting relationship, and they wanted to take images, but a good friend of mine on the Galileo team argued that the really interesting stuff was what was down here below the X. And that's where it gets interesting, and we call that Connemara chaos. So let's blow that up and see what it looks like. In fact, let me show you what we're going to look at. This bright thing here is this bright thing here. So now we've blown up, that's 10-kilometer scale bar. This is characteristic of places on Europa's surface. It literally looks like there's an ice shell which has lots of different linear features, ridges in it, has been broken into pieces. These pieces have been translated with respect to one another. They are cracked, they are tilted on edge like this one here. And then there's this sort of jumble of what looks to be kind of mush, except everything is frozen here now. And the obvious impression that image was taken back in 1996, I believe, is that the interior of Europa has burst forth, has literally broken the ice shell of Europa apart, and if not exposed the ocean to space where it boils and freezes, something very closely approximate to that, where it may be very soft, very warm ice, but it's extreme form of activity. And this is indeed why we call this stuff chaos. The color of the chaos is actually brownish. This white stuff here is actually ejecta spray from that bright crater, 1,000 kilometers to the south. Nothing stops the ejecta on Europa from traveling. The gravity is a little bit weaker than that of our moon, and like our moon, it has no actual atmosphere. It just has individual molecules darting around in a Maxwellian fashion. So we call that an exosphere. Sometimes it's easier to see the details in black and white, the color, the human perception with color. So I'm going to zoom in a little bit. So let's look at, here's this broken potato chip looking like thing here. And that's it in the center. So again, here's you get these, literally a sense of like icebergs tilting on their side. You get a sense that maybe the ice shell on Europa, at least at this part of this time in geologic history, was not necessarily very thick at all. But this is actually a major debate within the community. Some people think the ice shell, at least in the past, has been only a few kilometers thick, and other people think that it's on the order of 20 to 30 kilometers thick and has maintained that for a long time. And I say that because if you go into the literature and review chapter, where there's a whole volume on Europa. Actually, if you wait 1 second, I forgot to bring this prop. And so if you're really interested in Europa, there's this fabulous book, which is not focusing, maybe back on my face. Anyway, there it is, Europa. So I'm one of the editors that is filled with review articles about everything we know about Europa as of 15 years ago, and it hasn't changed vastly since then because there hasn't been any new spacecraft mission. But here's one figure from one chapter in there which talks about ideas about how chaos might form. And I'm not going to go through this, but you can easily see that some of these have liquid right at the surface or near the surface. Some of them simply have warm ice. Some of them are kind of in between where it's solid ice with a liquid layer. We actually don't know. And one of the things we're going to do with these new missions is look into the interior of the ice shell of Europa with sounding radar to try to find out exactly what has actually happened. I want to talk a little bit about what the discoloration is, because this gets to the chemistry, because if the ocean is interacting directly with the surface and bringing itself up, then we could maybe tell what's there by looking at at least the spectra. So this is a better picture of Connemara in the sense that the colors are better balanced. It's still a little bit intense, but basically it's brown, okay? So there's some brown stuff there. People often ask me, what's that brown stuff on Europa? A major class of possibilities has to do with sulfates, that is SO4 and in different cations. The sulfur might come from below. It might come from sulfate literally erupting out of the ocean, or it actually might come from above, because the innermost moon, Io, is covered in sulfur and sulfur dioxide, and it has actively erupting volcanoes, and these volcanoes spew material into space, and they fill the Jovian magnetosphere. And so sulfur atoms are continuously bombarding the surface of Io. And so when you add sulfur and water ice, S and H2O, and you basically churn it up, when this is charged particle radiation, you're going to make sulfuric acid hydrate. Now there may be something else there. Magnesium sulfate hydrate is one of the favorites of spectroscopists who study Europa. And what I mean is that we have spectra in the near infrared. The x-axis here is a little beyond the human vision, 1 micron to, let's say, 2.5 microns. And this is the dots are Galileo data, and the lines are laboratory spectra. And on the left, you see literally hydrated sulfuric acid, frozen sulfuric acid mixed in with water ice. And then on the right side, it just says frozen brine, but this has a bunch of either carbonates and sulfates in it. And it's this sort of stair-step pattern of absorptions that's characteristic of a distorted water ice lattice. I have to say, just in case you don't know, magnesium sulfate is actually a common material that, at least in the US and probably in Europe, you can buy as a laxative, okay? Epsom salt, this is magnesium sulfate. So I hate to think of what sort of trouble Europa might be in, but that may not be the actual answer. One of the most recent lines of evidence that people have been working on is to actually consider the radiation environment. I don't mean gamma radiation, I mean the charged particles that come from space, but they deliver a lot of energy to the surface. And if you simply take ordinary salt, table salt, you'll generate color centers and you'll darken it. And it's not implausible that salt could come out of the interior of Europa. And in fact, when I mentioned this exosphere, these atoms that are, we can actually see, because the in resonant fluorescence from in Hubble data from Earth orbit, we can actually see sodium and potassium. There's a halo of these atoms around Europa. So they may come from a salt. And so here's just a picture made by my colleague Kevin Hand at the Jet Propulsion Lab. That's table salt, coarse table salt, and it's been bombarded with helium atoms, if I remember correctly, and it's turned brown. Now it doesn't, otherwise you might say, well, why didn't you see this in the infrared? Salt doesn't have absorptions in the near infrared, so we're actually looking at visible color centers. So it's kind of tricky. That's why it's hard to identify ordinary alkali halides in outer space unless you have the individual atoms. Here's another study by Carl Hibbets at the University of Colorado, which he looked at a whole bunch of different salts, and he zapped them with, I forget, and then waited a while because these color centers can heal. As an example, you could have potassium chloride, which we use in rock salt to keep our roads free of ice in the winter here in St. Louis, and it turns magenta or purple. Europa is not purple, so it's probably not the answer. But and then down below here in the lower right corner, you see it actually fading to a kind of lavender. Carl thinks the best example, like table salt gets too brown. You can see this one down here in the very bottom, NaCl. But if you take magnesium sulfate, it begins to actually look like the real color of Europa. So that's what Carl likes. He's one of the people on the sulfate bandwagon. But anyway, I think we are getting to the point where we might actually have some idea about the materials that are coming out of the interior. So let's talk about those linea, since we've talked a little bit about chaos. This is nice because we don't, one of the things about the Galileo mission is that its antenna was broken. It's a Pie-Gate antenna. So we actually have much more limited data. So if we took the data that we wanted to take in the 1990s, we wouldn't necessarily have to go back. So we have tantalizing, but incomplete clues. But we do have some nice pictures of this particular linea right here. And so I'm going to zoom right in. It's called Androgeos linea. You don't have to worry about the name. And that's what it looks like when we get really close up and personal. It's a crack that runs through the surface of Europa with a double ridge that's a few 100 meters high. And it seems to be surrounded by kind of diffuse material that is filled in this much more complicated set of ridges and troughs that are all surrounding it. In fact, when you look at these plains on Europa, it almost as if there's just one lineament after another. It's like a ball of string. When you wrap string around in a circle and it goes round and round and round, it's this completely mad overlay. But they seem to get fainter and less tall with time. And so the most recent ones look like this. And you say, well, is this a constructional feature? Is this some sort of linear volcano? Some of these things go on for hundreds or even over 1,000 kilometers. It's hard to believe. We don't really know. The leading idea, I have to say, has to do with tectonics. That is the deformation of the ice. Remember, it's ice, solid ice. The surface is 100 Kelvin. It's cold, but down below it can be warm. And the moon is geologically active. It has its own heat engine. It has its own heat coming out. And it undergoes powerful tides, regular squeezing in its eccentric orbit around Jupiter. And these tides can push a crack one way. And then later in the orbit, the crack can move in the other direction. And then it can reverse and it can keep going back and forth. And so one model for what's going on these lineaments is that's literally cracks rubbing against each other and getting warm and thermally expanding and warping upward, maybe with it. But other people think it's actually, it's accompanied by eruptions of material. Now, we haven't seen any eruptions, but we're looking. Well, we have looked. Let's keep going. Now that's just one crack moving back and forth, making a ridge. There's all sorts of stuff on Europa. Here's just another piece of Europa. Here are some lineaments and they're more little arcuate segments running across the surface. But you can see in background, there's a kind of almost scythe shape or triangular, arcuate triangular shape. And we call these, they look like wedges of a, slice of maybe a pizza or something like that. And these were seen by Voyager. And these were interpreted, in fact, by a student of mine, Paul Schenk, as openings in the crust that literally lead, not just sliding back and forth, but permanent opening and rotation of the surface of Europa. A very controversial idea in the 1980s, but absolutely proven by Galileo. This is that same region. This is a reconstruction by Rob Sullivan of Cornell University in New York State. And you can basically rotate pieces. It's like a jigsaw puzzle, like Humpty Dumpty in the European fairy tale. You can put Europa back together and realign things, and you can kind of build a history of tectonic motions. So crustal spreading. If you have expansion, if you have things moving apart on a body of basically fixed size, and this happens on the Earth, then you have to have some way to take up that new area elsewhere. And that's also a big debate. One of the leading ideas is that there are, in fact, zones of convergence, like the mountain building regions on the Earth, like the Himalayas, and Tibet and so forth. But given that Europa is an icy body, you're not going to get towering rock mountains. You'll get kind of maybe low levels of some sort of ice deformation. It's not obviously prominent, but Simon Kattenhorn and Louise Proctor published a paper back in 2014 where they argued that if they do a reconstruction, here's just a piece of Europa, and if they do a reconstruction like I was just showing you what Rob Sullivan's work of lining things back up, they make this, oops, let's go back. Trying to go backwards. There we go. They make this on the left, looks like this on the right in the past, but it's not just a question of moving things together. They're moving to make this fit. They have to move this piece away from this piece. It moves apart. So this is what it says here. Total missing area is almost 100 kilometers wide. So they actually consider this to be an area of geological convergence. And they at least proposed that there is some analog to the subduction system that exists here on the Earth, in which the Earth's plates return to the Earth's mantle. Now on Europa, we're talking about a floating ice shell of uncertain thickness, and we don't know whether this is a convective driven process or simply a tidally driven process. It may be a much more, not quite so dominant. It might just be an effect of the tidal geology, tidal tectonics of Europa, and not the primary driver the way plate tectonics is for the operation of the Earth's geological engine. But this is a cartoon from their paper. And this is the kind of thing that, again, we want to explore by returning to the satellite. Now, of course, this is all geology and maybe geophysics to you, and they say this is fascinating, but is this really why we want to go to Europa? Well, I'm getting there. Here's one more, just a little bit of evidence. This is actually a pretty nice picture. This is probably the best natural color version of Europa using all the image data that we've taken from spacecraft. And this is, it's a variable resolution. So you'll see some things look pretty detailed and some things look funny. But this is the natural color of Europa. So it's a pale, washed out with yellowish and brownish region. So here's that bright crater. The X marks the spot where we looked at Connemara chaos is over here. The wedges we just looked at are over here. Now, let's take this and jack up the color. So my former student, Paul Schenk, did this for an atlas he published. This is a beautiful book, by the way, The Atlas of the Galilean Satellites. It's almost a coffee tale book, except it has every geological image taken by the Galileo and Voyager missions of the Galilean satellites. And you can make a book out of it because there are not that many pictures because the mission suffered from its broken antenna and had to send everything back at a terribly low bit rate from the low gain. But anyway, here's an exaggerated version. You see very strong dominance of chaos in 2 areas, and then lots of lineaments in another area. And this is just the way Europa looks. But if you shift the globe of Europa, let's say 30 degrees to the north around a certain axis, you make this thing look like this, and you all of a sudden of California and Santa Barbara have argued that this symmetry is a better signature of the tidal stresses generated in the floating ice shell of Europa as it orbits Jupiter, and that on its own, the fact that this shift makes it more symmetric in this very global degree 2 sense argues that there's literally true polar water, that the entire ice shell of Europa has shifted over time by on the order of 30 or more degrees. So it's a very mobile world on almost every scale imaginable. As I said, the lineaments are fault controlled structure, but now I want to ask, well, what else can we say about the ice shell? Let's look deeply. We're going to zoom right into a little tiny area between these lineaments where there's little tiny dots, if you could see on your computer screen. And when you blow that up, well, there are the lineaments, and you can see the lineaments are discolored and brownish. So stuff is coming out of the inside of Europa on those lineaments, almost certainly. And these little spots are themselves discolored, or some of them aren't. They're actually pits in the ground, maybe a few hundred meters deep. And you can see that it literally is it's just subsided. Nothing has happened. Some of them are just literally the ground has dropped away. And then some of them are disrupted and filled with little bits of stuff, and they're miscolored. And so sometimes we call these things, well, they can just call them spots or lenticulae in Latin, but they're also perhaps what we might think of as micro chaos, little tiny chaoses. I had a student working with Paul, Kelsey Singer, and she went through all of these pits on all of the good data we have for Europa, and you can use a technique called photoclinometry and also stereo imaging if you have enough images to determine the depths of these pits. And you see some examples here on the left of literally depressions in the ground where the original surface has simply subsided, okay? And on the right, you see other effects where you see stuff has somehow pushed the landscape up or bubbled up through the surface. Or this very interesting one down here, a few kilometers across, is a smooth little patch as though something liquid has flowed out into a depression. If we plot all those depressions and interpret them with Archimedes' principle, or the law of isostasy, you can determine what the minimum thickness of the ice shell had to be, because it can't be, it obviously has to be thicker than the depth of the pit. But if you think of, if this is ordinary water and this is ordinary ice, then a certain pit depth implies a certain uplift of the ocean. And that is this solid line over here. And so for pit depth between 3 and a little closer to 500 meters, we get minimum depths of the ocean, of the ice, minimum thicknesses of the ice shell when these things are forming of 4 to 6 kilometers. So that's a minimum depth, and I think that's fine. Now, of course, we don't really know what the composition of the ocean is, or even technically the ice shell, although if the ice shell forms by freezing of an ocean, like on the Earth's ocean, it probably expels any salts or sulfates or whatever, and it's probably fairly clean. But the ocean can have all sorts of stuff in it, and that expands the parameter space. But I think it's probably a good estimate, several kilometers thick at least, maybe 5 or more. There's a more direct way, and I wish we had better data, maybe in the future. There's a more direct way to try to probe the thickness of the ice shell if you don't have instruments, and that's with not just these naturally occurring pits, but with impact craters. So here's another graph that, again, this Paul Schenk did this work on his own well after he got his PhD. And what he's plotted here are the depths of craters on Europa. and they're labeled in certain ways. The thick, dark curve is the lunar curve, depth diameter, and a simple bowl-shaped crater, just like any hole in the ground, the common garden variety crater has a what we have a depth diameter of on the order of ratio of 1 to 5. And that's true on the moon, and it's true on Europa. And when you get to a big enough crater on the moon, you start to see modification to the shape. So the craters become flatter, they develop central peaks. They look like Copernicus or Tycho or the famous big craters on the moon. I don't mean filled with lava. I mean, they're just flat on their own, like pie pans, not bowl shaped. You know, crater means bowl in Greek. On Europa, simple craters are also bowl shaped, but they transition to these complex forms at a smaller diameter at a more shallow depth than on the moon. And that's to be expected because the gravity is similar to that of the moon, a little bit less, but it's similar, but ice is weaker. But the interesting thing about Europa is that as you start to push to not very large diameters, but 10 kilometers and above, the craters start to continuously get shallower and shallower. And those two large craters I mentioned to you are they basically have very little topography on them. And that is in terms of a mean depth. There's lots of rugged, small scale topography. This is interpreted. Paul interpreted this as the signature of impacting into a floating ice shell in which you begin to interact with the water, and it makes the overall structure much weaker. Now, you'd like to do this quantitatively. Veronica, and the answer from a quantitative analysis is that the shell, when these craters were made at least, was on the order of 10 or more kilometers, but there's a wide error bars. But again, I have to stress that there's really a great uncertainty in this. We can make these measurements of these craters very, very well, but we cannot simulate them very, very well because we don't know everything about impact physics. You might think we know a lot. You see a lot of calculations sometimes in literature, but there are a lot of tunable parameters, and you really have to know what you're doing. Otherwise, your output is just garbage compared to what you put in. Here's the paper where that result comes from, where the dots are Paul's data and these lines dashed and solid are simulations assuming ice shells of various thicknesses. So this dashed line is 20, this dashed line is 10, this solid line is 7, and this dotted line is 5. And Veronica and her co-authors, including Paul, decided that in order the best fit to this data set was a little bit on the order, a little bit overall, because you can see that it underpredicts down here and it overpredicts over here. Overall was on the order of 12 plus or minus 5 kilometers. The fact that there's not a good fit tells me that there's some problem. Is the problem in the data measurement? Is the problem in the numerical model, the so-called ice sail model that is being used? Maybe a little of both. So I would say I'm putting a question mark on this, but I would say that the crater data on Europa will ultimately be very telling once we are satisfied that we know how to simulate properly all the way to what we call the late time, the actual, when all the mass motion cease of crater formation in ice. It's kind of a forefront because there really aren't examples, even explosion examples of the proper scale to calibrate this stuff. There's a lot of data, a lot of work on explosions in rock for reasons I don't need to go into right now here on the Earth, but there's a whole lot less known about the response of planetary ice on a geological scale. I'll just mention that the very biggest impacts on Europa are not that big. This thing called Tyre is only 150 kilometers across, and really the crater is in the center, and what you see is a surrounded circular or arcuate pattern of ridges and in some cases troughs, which are structurally bound, and we call these graben. So these are ring graben. And this is a characteristic of impacts into thin, brittle ice shells over either water or very warm ice. And we see these kind of structures on much larger scales on Ganymede and especially on Callisto. But this indicates to me that this is a very warm body on the inside. That is, you don't have to go too deep inside from the cold surface of Europa to reach very malleable ice that has the viscosity of glacier ice on the Earth, and then perhaps even water. And I could say more about this technically, but in the interest of time, I'm going to move on. Let me just sort of summarize. We've been looking at a bunch of geological features on this satellite. Here's a map of a recent map, a sort of global scale look at Europa. And basically the greens are chaos, and they're concentrated at the sub and anti-jovian points. Actually, they're concentrated at the leading and trailing positions, because these satellites, Europa, like our Earth's moon, it circles Jupiter in a tidally locked state. So one face of Europa always points at Jupiter. So it's not evenly spread out, all the chaos. There are sort of like chaos regions and lineament regions. And there's the wedges here in the middle here. I want to talk about two little blobs here. They're dark green, and that means low albedo chaos. And they're really low albedo chaos. And here's an old, I think a picture disappeared. Must have gone somewhere. Anyway, I'm sorry, it fell out of my slide set. And anyway, these are those low albedo blobs. I was going to show you a different picture that really shows how dark they are, but this is what they look like in color. And they're called Thera and Thrace. That's their scale. They're tens of kilometers across, and they're rugged chaos regions, and they're quite distinct in their color. And so we think they're quite young. And this is a good opportunity to mention that the surface age of Europa, or to reiterate, is quite young compared to the billions of years age of, let's say, the moon, or even the outer moons of Jupiter, Ganymede, and Callisto. And in particular, this one, Thera, because of the deformation in the surface, it has been, people have written papers about this, is it's an actively deforming region. So it's one of the real targets for upcoming exploration. I wanted to show just a close-up view of Thrace, which doesn't get as much love, but we're going to look toward it down here. This is a black and white photo. This again shows you the albedo. It also illustrates, you can see some of it looks very sharp. That's because there's an actual high resolution image nested in lower resolution images. So we don't have the whole thing. It's clearly chaos-like, but you can see there's sort of like this dark pattern as though somebody has spilled motor oil or dirty water on a concrete floor, and it's run down in rivulets. It's almost as though some sort of dark liquid has erupted on the surface, which I think is quite plausible. It may not have been dark when it erupted, but then it gets radiation processed. And so what's the secret? Why is all this going on? This world is smaller than our moon. It's so active. Well, part of the secret is we're looking at ice. It's easier to mobilize ice. You don't have to get to be that hot to melt ice compared to rock. But the real secret is that the innermost moons are all in this tidal resonance, this famous 1 to 2 to 4 period resonance of the orbits discovered by Pierre-Simon Laplace and named after him. And this is how it works. They go round and round. And if you look very carefully, you see that each pair, let's say Europa, they meet up at the same place, Io and Europa at the top of this figure, and Europa and Ganymede at the bottom of the figure on a certain period. And this repeating cadence continually pumps the eccentricities, continually distorts the orbits of these satellites so that they have tides. The tides then flex and generate heat. And this wants to make the orbits more circular, but because they're in this resonance, they can't get circular. So even though Europa's eccentricity is not very large, it's large enough that it's continually kneading its surface and kneading its interior, kneading with a K in English, and this generates energy. It's the same, and the same energy is going into Io at an even more prodigious rate, and it drives the ongoing and continuous volcanism on Io. Now on Europa, here's a cartoon version. because Europa is in an eccentric orbit, it's as it goes around Jupiter, it's not exactly, it's slight, it speeds up and slows down ever so slightly. And Jupiter appears to move in the sky. These are actually, this is a not, the stars in the background are not artistic license. They're the actual stars that you would see if you were floating with Europa this way. And if you could cut away Europa and exaggerate the distortion, this is what it would look like. It would be flexing in and out and oscillating back, nodding back and forth, or librating back and forth with respect to Jupiter. And if you look carefully at the animation, you see that there's kind of a pulsing bit of red inside the shell, the ice shell, and also pulsing red in the rock. So there's tidal heating in the ice shell and tidal heating in the rock. We don't know the exact balance, but there are models that some say all of the heat really goes into the ice, which makes it thin. And there are other models that say that some of the heat's in the ice, some of it may even be in the ocean in tidal dissipation, but also in the interior of Europa. And that dissipation in the interior may drive not Io level of volcanism, but may still drive a kind of volcanism on the inside of Europa, which is very exciting. Because if Europa has an ocean, hopefully, if you don't know this already, hopefully I've convinced you that everything points to this ocean existing. It also has strong tidal heating. If it has an ocean, it means that there's a seafloor, and if there's strong tidal heating, there might actually be seafloor volcanism. And this is not a picture of Europa, obviously. We don't have anything like this. This is the Earth seafloor near a mid-ocean ridge where we have active volcanism, and you have hot water being pumped through volcanic rock, erupting into the cold seawater, and in this case, precipitating iron sulfide, so-called black smokers. And this is why people are excited about Europa, that it has a seafloor, and it's an active body. And if we look at the history of life on the Earth, and here's a so-called tree of life, or at least an older version of the tree of life, where we have the three kingdoms, bacteria on one side, eukaryotes, that is bodies made of single or multiple cells that have nuclei like us. And we're out here at the edge of this thing, animals, fungi, and plants. And then the sort of primitive kind of life called archaea. And this is the interconnection of the branches. You kind of go back in time towards something called Luca, the least universal common ancestor. But the important thing is that if you look at the names of these things that are down near the base of the tree of life, they have interesting names like thermotoga or aquifex or thermoproteus or pyrodictum. All of these things that indicate heat. Heat-loving organisms, organisms that live in environments like you see with the black smokers. That is, in fact, they are chemosynthetic organisms. Some of them use carbon that filters down from the surface photic zone of the sea, but many of them actually can build their, all they need is a source of carbon. That carbon can be CO2, that carbon can be methane, and they use the chemical disequilibrium at the Earth's seafloor to power their metabolism. So the scientific interest in Europa, as fascinating as its geology is, as fascinating as its geophysics is, as interesting as it is from an exoplanet point of view, as part of a system of small planets close to a massive parent body, the real driver to explore Europa is that there's a massive body of water with an unknown composition, an unknown thermal input, and the possibility that life may have evolved far away from the Earth in an entirely new and different environment. So that's really why we want to explore Europa. I think I'm going to run out of time, so I'm going to skip over the possible evidence for plumes. A lot of the active geology on Europa, or at least is active in a sort of historical sense. The question is there anything happening right now? And we see elsewhere in the solar system and the moon Enceladus around Saturn, active plume eruptions. And we have tantalizing evidence for plume eruptions on Europa. But I'm going to leave that alone. I could talk about that in any questions if we come back to that. It's a possibility, but it's unproven. What are we going to do? What are we going to do? So let's get on to the final part of the talk. We're going back. The European Space Agency has a mission, which I'm privileged to be part of called the Jupiter Icy Moons Explorer. And what you see actually in the foreground here is the largest moon in the solar system, Ganymede. This is a mission that whose ultimate goal is to orbit Ganymede. This will be the first satellite orbiter in human history. But it will make 2 close passes by Europa, and it does have a complement of instruments that will learn things. It's being built now, and it's almost finished basically, and it's scheduled to be launched next year. So I'm not going to talk much about that. I'll mention that in a little bit. What I really want to talk about is NASA's mission, so-called Europa Clipper. Both of these missions are solar powered. That's the way technology has developed to this point. The Clipper is going to have 5 solar panels on each side. It's going to carry its electronics in a vault, not a lead-lined vault, but a titanium vault that will help protect all the electronics from that fierce European radiation environment. You see the high gain antenna at the top here, and it carries a bunch of instruments, and it carries this thing sticking out is not a telescope, it's actually a boom for the magnetometers to make very detailed magnetic measurements at Europa. And these wires or antennas that are sticking out are part of the radar sounding system that I'm also privileged to be a team member of, because this is really the great, not only we're going to take all the sort of every picture you can imagine of Europa as we fly by it, but we're actually going to look inside. The science goal, the main science goal of the Clipper mission is to explore Europa, to really explore it with a full suite of instruments. It's a major mission, and to investigate its habitability. And I mean investigate its habitability. It's not a life-finding mission. The instruments aren't designed to look for life per se, but we want to understand as best as we can the context of what's going on out there. Because we know there's water, we know there's interesting chemistry. I hope to convince you of that. There is energy that must come from surface radiation, from the geology on the inside. And so we're going to be basically testing different kinds of habitability hypotheses. And this sort of, the cartoon on the right there shows you all sorts of things that could be going on in the deep interior of Europa, an interaction with the ocean, interaction of the ocean with the ice shell, things going on inside the ice shell, and things going on at the surface. And in fact, it even has a plume. Of course, it's a fantasy at this point, but it might actually come true. As I say, it's a major mission, and basically we have 10, or if you like, 11 scientific instruments. The green ones are called remote sensing instruments, and they're, first of all, if you're going to fly to another planet, you would obviously take cameras. And so we're going to have cameras that cover the bases in terms of wavelength. There's a ultraviolet spectrometer, which is actually a good thing for measuring that exosphere and for if there are plumes, detecting what they're made of. There's a very sophisticated camera system, cleverly named ICE, the Europa Imaging System, but ICE, of course, means ice in German. And so there's a narrow and a wide angle camera. There's an imaging spectrometer. So we're going to look into the infrared even farther than Galileo did, and it'll be a modern solid state device. And so we'll get much better infrared spectra, and we should really be able to tell what we're looking at, which was, as I say, was still controversial even today. And we're going to go farther into the infrared with a thermal imager, and I'll show you a little bit more about that in a second. And in terms of remote sensing, we also have the ice penetrating radar called REASON, and I'll explain what that means. I'm also privileged to be part of the gravity team, because obviously you track the spacecraft, so you get Doppler tracking. So it comes for free in a way. So it's not a separate instrument, it's the communication system, but it's very important to understand the internal structure once and for all of Europa, and that'll come from the radio data. Now, since we're going to be flying quite close to Europa repeatedly, we have instruments to measure things on the spot, in situ instruments. We have a mass spectrometer that looks at individual atoms and molecules, and I'm privileged again to be part of that team. And that's just for gas. There's also a specialized mass spectrometer that looks for dust, and I'll explain a little bit about that. So there's bits and pieces that come off of Europa. You can tell what the surface of Europa is made of from these solid particles as well. The magnetometer is, you might think of it as a remote sensing instrument, but it also measures all the local magnetic properties because of the Jovian environment is very complicated. So in a sense, that's an in situ instrument, and part of the measurement suite to understand the magnetometer data will come from measuring the plasma environment, and that's the so-called the PIMS instrument. There's also instruments to measure the radiation dose, which is an ancillary bit of instruct. It's important for spacecraft health to know what the dose you're getting, but also tells you more also about this, about the environment that the surface of Europa is being subjected to. I'm not going to go through all the instruments. Let me just show you. The interesting thing about this mission is that it's not going into orbit around Europa. It's a very dangerous radiation environment, and we, the NASA and the scientific community here in the US, we've developed this interesting scheme where we go into orbit around Jupiter and then repeatedly go by Europa. And what you see in all these colored lines are all of the orbits. Our plan actually is to launch, we're building the spacecraft now, is launch in 2 years, in 4 months, in October of 2024. We're not going to, the spacecraft is so massive, even by, we're going to launch on a, what's called Falcon, SpaceX Falcon Heavy, non-expendable version. And it's still going to take a while to get to Jupiter, about 6 years. That's because we're not going direct. The trajectory is called MEGA, and that means Mars Earth Gravity Assist. So we're actually going to go to Mars first, come back to the Earth, go by the Earth again at a low altitude, gather up a little bit more velocity, and then head on out to Jupiter. And then we're going to go into orbit around, resonant orbits around Jupiter, and we're going to encounter Europa dozens of times in the prime mission, 49 individual flybys. And if there's an extended mission, we'll just keep doing that. And we'll gather all sorts of data. Let me show you what that looks like. So it's designed to look at Europa in as many different aspects. So these are the 49 trajectories. This is our chosen trajectory. This might get tweaked or modified, but we're actually working to this set of flybys. Because of the geometry of the orbit, we have to come in and either skim the sub-Jovian point or the anti-Jovian point. So we don't get as much low altitude coverage over the leading and trailing positions on the satellite as it orbits around Jupiter. And these are the traces of the individual passes, and these they're color coded so that the hot colors like red and orange are the lowest. And I see I've run up to the hour, so I'll try to rush along and not keep you too long. So there are lots of low altitude flybys on the order of 25 kilometers, and then we'll still take data as we're higher. Some instruments actually work better at a higher altitude. The radar does. It doesn't get as, you get a better sense of the topography nearby. So I'll just skim through. So we're basically going to fly over Europa and look at all of this fabulous terrain, changing from plains to wedge regions and lineaments and chaos. And what are we going to do? Let me just tell you just a few things about 3 of the instruments that I find particularly fascinating. The thermal imager, we've never flown one of these to an icy moon. And so we're actually going to look for the heat signature of active areas. So I'll just say that. So you can see the filter range goes out to 70 microns. And so here's a simulation of a ridge here. What if that ridge is active, like a vent, like on Enceladus? We might expect to see a heat signature down the center. The radar, 2 frequencies down here, dual for 60 megahertz and 9 megahertz. So in vacuum, that works out to be a wavelength of 5 meters and over 30 meters. So this is, we're really going to not worry about the surface so much. We're going to go deep, and we are going to look for that ocean. We're going to look for we're going to send a radar wave in and look for the attenuation that is characteristic of a hot ice, and look for that ocean, but also any other structure. It's really a reconnaissance. It's an exploration of the inside of an icy world. And I have to say, there's a heritage here. And if you've never heard of this technique, we use radar usually from airplanes. We we sound the entire depth of the Greenland and Antarctic ice caps. The radar systems have been flown to Mars on the Marsis and Sherrod instruments, and we have looked all through the ice caps, the north and south polar caps of Mars. The European Space Agency flew a radar to the comet 67P and in the Rosetta mission, and because there was a comet lander, a separate satellite, they could do radar sounding of the inside of the comet. And we're going to do the same thing, not for the entire inside of Europa, but down to many kilometers with these two different frequencies. And I should say reason stands for radar for Europa assessment and sounding ocean to near surface. So that's a very tortured and convoluted acronym, but that's what it stands for. And there's an equivalent system. It's only 9 megahertz on the JUICE mission, and that's called RIME, Radar for Icy Moons Exploration. And both of these radar teams are highly complementary. Many of the same members in the US and Italy are on these teams, including myself. So we'll be looking at all of these icy satellites through radar. Oh, here's that missing picture. It somehow dropped into a different part of the set. But that's what I meant by it's a low albedo stuff. You can see this Thera and Thrace macula down there. The other instrument I wanted actually two, but they're related. One is a mass spectrometer. And again, it's designed to look for what is coming off of the surface. And you might say, what? You can actually get enough stuff to analyze? Well, actually, it turns out you can. The surface, and you have photo sputtering, and you basically have a halo of atoms. And if we're so lucky to actually find a plume, an active plume on Europa, it'll spread around the surface, and we'll be able to fly through this stuff. And the mass resolution and the dynamic range of this particular instrument, this mass spectrometer for planetary exploration, or mass specs, is phenomenal. And we're really interested in what we hope to learn from the chemistry of the material that comes off the surface, because we should be able to tell what kind of ocean we have. Given the time, I won't belabor this, but I'll just tell you that the ocean's chemistry could be controlled by the rock interior and therefore be reduced in a chemical sense, or it could be controlled by the radiation effects on the surface ice, which generate free oxygen and hydrogen peroxide, which is very oxidizing. So, and that may flux into the ocean. So we may have an oxidized ocean, we may have a reduced ocean, or we may have both. And that imbalance may in fact be what allows biology on this world. So we may have a biological ocean. So determining what's in that ocean and what the chemical speciation is a key goal of the mass specs instrument and of the following instrument, which is called SUDA, because it turns out that individual dust particles, there's micrometeorites that bombard Europa and they drive particles off, and then these will fly into the instruments because we're going to be flying over the surface at 4 to 5 kilometers a second. And so this will vaporize the particles, and then they can be analyzed in a time of flight mass spectrometer. And in fact, the SUDA team, which is led by Sasha Kempf at the University of Colorado, has modeled that there's basically 100 micron size micrometeorite impacts coming from outside Jupiter's orbit, really continually bombard Europa and basically put little particles into these ballistic trajectories. And that SUDA at 25 kilometers will actually detect 40 of these particles a second. And then they can figure out then what the salt is in the particles from the surface. And in fact, whether there are any complex organics. So that's totally fabulous. And of course, if there is an actual plume being driven by boiling water, then that is the jackpot that we all hope to be able to directly sample with these mass spectrometers. So that's the story of why Europa is fascinating and what NASA hopes to do. And if you want to read all about it or more about it, there's a website. You just have to type in Clipper and Europa, and you'll probably end up at this website. Thank you very much. And I do apologize for running over it. So I have this
Okay, thank you very much, Professor McKinnon, for this very exciting and enlightening talk. Yeah, it's great to know, this very exciting development in your field. And I hope, this project, this Voyager project will run very smoothly. Although, probably need a little bit of patience, right? 6 years to get there.
Yes,
Yeah.
yes. So, I'm planning on being alive, but there are a lot of younger members of on the team as well, because I started working on icy satellites decades ago with the Voyager mission. So I'm sort of now somehow I woke up and I'm a senior scientist. I don't know. It happens.
Okay. Yeah. Now, yeah. So this session is open to questions. So yeah, anyone, please just speak up, unmute yourself, and ask Professor McKinnon any questions.
Hi, I have two questions. So my first question is, how do you find evidence for Ganymede and Callisto having subsurface oceans? Because I heard a while back that those two moons also have subsurface oceans, but I thought those two were rock-based and not ice-based like Europa.
They're much more icy, but we have that same kind of evidence from the magnetometer to Galileo.
Oh, okay.
But let me just say that there's a controversy about Callisto, because Callisto has actually a picobar level CO2 atmosphere and an ionosphere. And therefore the conductivity above the surface of Callisto. And the question is, does Callisto really have an ocean, or is the ionosphere fooling us? And Ganymede has its own internal magnetic field generated, we think, by convection in an iron core, liquid iron core. And so there's a possibility that we don't have as good evidence as we would like. Neither Ganymede or Callisto are geologically active in the sense that Europa is. But we'll learn a lot more from the JUICE mission. And both of these missions, well, JUICE in particular, but both of these missions will have multiple passes by these other satellites simply to trim the orbit to get down, for us to get down to Europa. So there is an opportunity to do a lot of Ganymede and Callisto science, though right now we are forbidden to talk about that because it costs money.
Oh, so my second question is actually might be forbidden, but I heard you were part of the New Horizons team.
Mm-hmm.
So there's another dwarf planet called Sedna. I believe currently it's the furthest dwarf planet we currently know of. And I saw the launch window to arrive, but to get to Sedna at its closest orbital perihelion is by 2035. Will there be any plans by that time to send a spacecraft towards Sedna, so for analysis and study?
I think Sedna is incredibly far away compared to.
Yeah, it's the furthest planet from this. This is currently furthest known dwarf planet from the solar system.
Yeah, there's no particular plan. So let me encourage the Chinese Space Agency to develop one.
So if there was to be a plan, how much time do we have before to build the spacecraft and to get into launch, a year or two?
Without looking at, I know people have actually tried to calculate the possibilities. What you would like to do to visit any of the dwarf planets, whether it's Eris or Sedna, or even go back to Pluto to get a good look at the other hemisphere the New Horizons didn't see, is you'd want to arrange for a Jupiter gravity assist.
Yeah.
So those come around periodically.
Is there a possibility for Saturn or Uranus or Neptune assist as well, or is that already too far away from the sun?
You'll get less bang for the buck. You won't get the kind of grand tour effect that you did in the 1970s and 80s, where all four planets were in a sort of almost magical alignment. And then but that would be one way of shortening the flight time. But I still think you have it's probably it took New Horizons from lifting off from the Earth. It took 9.5 years to get to Pluto, and Pluto was very close to its closest approach to the sun when that happened. And I would say that a mission to Sedna is going to be longer than 20 years. And so you'd have to have a very long-lived radioactive power source.
Do we have technology for that now, or is it not available?
So please take it up. I don't.
Sorry, I got one more question, last
Okay.
one. So you know how Saturn has the moon Enceladus? Can some of the technology on this satellite be applied to Enceladus as well?
So I'm sorry, I got a phone call that was just distracting me. Can you repeat the beginning of your question?
So some of the instruments on this spacecraft can they be applied to other spacecraft that can fly?
In fact, in a sense, these are are instruments that have evolved and are even more powerful than the instruments that were on Cassini. So like same people on the ion and neutral mass spectrometer for Cassini, which I worked with a little bit, are behind the mass specs instrument. But mass specs is a far more capable instrument. As an example, the INMS on Cassini was designed to study the atmosphere of Titan. That's why it was on that mission. They didn't know that they would actually be exploring Enceladus and flying through the Enceladus plumes. Now, this instrument is in fact designed to do that. But if you want to go back to the Saturn system, you would want to carry more powerful instruments. You would want to carry a sounding radar to Enceladus.
All right. So sorry, last one. I got one more. So would you say the moons of Saturn and Jupiter are more a priority for study than the Uranus and Neptune? Because Uranus and Neptune haven't had any like planned launches compared to the other moons.
There are, for different reasons, they have different priorities. So we've done an incredible job with the moons of Saturn with the Cassini mission. So to go back and just quote study them is not the best use of our technical and financial capabilities, but their targeted approach to go back to Titan, the big moon. This is what people want to do. And in fact, there is a mission being developed in the U.S. called Dragonfly, which is a submarine. No, it's an aerobot. It's basically it's a quadcopter to fly. Titan has a thick atmosphere, so you can actually fly around. Now but the Uranian system is basically, we know comparatively little about it. We had one fly through in 1986 by Voyager 2, and the geometry was such that you could only see half of the satellite surfaces at all. So it's a really ripe target for new exploration. And similarly, Triton is a fascinating moon of Neptune. It's actually a captured Kuiper Belt object. It's geologically active. So we would learn more first order things about the Uranian and Neptune systems by going back, whereas returning to Saturn is a sort of follow on. Well, now that we've seen that there are plumes on Enceladus, what do we want to do? And in fact, what we want to do is we want to go sample that plume material and make as many measurements as we can.
Yeah, because I heard that there's actually this like plan about like sending the Cassini all the way from Saturn to Uranus towards the end of this mission, but it didn't follow through.
That was, I think, technically feasible, but it wasn't clear that the spacecraft would last long enough. What they decided to do, though, they had an opportunity to use Cassini to not move out away from Saturn, but to move closer into Saturn and to get measurements of the rings, and in fact, even drop the orbits inside the ring system of Saturn and perform detailed measurements of the magnetic and gravity field of Saturn, which could not be accomplished in any other way. And that also then meant that the ultimate fate of the Cassini spacecraft was to burn up in the Saturn atmosphere, which it did.
So even if Cassini could survive towards Uranus, they'd rather study Saturn rather than another new body.
Yeah, it was judged that it was a long shot for Uranus, and it would be a better thing to get new data for Saturn.
All right. Thank you so much.
Sure.
Okay. So, any other questions?
Yeah, Bill Manhoy.
Manhoy.
I was wondering why, in the case of Europa Clipper, that it is not going into a bound orbit around Europa, but the Jew satellite is going into a bound orbit around Ganymede. Well,
it's all about radiation. So the environment at Ganymede is much more benign. So it actually would be easy for us. It would be much easier to design a mission to orbit either Callisto or Ganymede. Whereas you could get into orbit around Europa, but it was estimated that the continual radiation bombardment would lead to a lifetime of the mission of maybe you'll be lucky to get 30 days. And so what we're doing with this mission is by only dipping our toes into the radiation field, so that even after 50 flybys of Europa, the radiation dose is only about 3 megarads in those appropriate units. It also, the cadence of science would be so rapid if we were in orbit around Europa, it would actually be difficult to deal with. The radar will generate an enormous bit rate. And it's not something you can compress and send it, if you can losslessly compress it, but it's still a lot of data. Whereas the actual, what we're going to do, we're going to be in these orbits where we're going to be, it's going to take us maybe 2 weeks or 3 weeks to come back to Europa every time. And so we will take a lot of data. Every instrument will be on. And then as we're on the outbound parts of the orbit, that's when we send the data back, including all that radio, all the radio sounding data. So it's actually necessary, you know, and we'll get a good high bit rate. So it actually works to our advantage. Then the mass spectrometer has a trick. You might think that the exosphere of Europa is quite dilute. You'd be right, but we have a cryo trap. We have a cold trap on the instrument so that we can collect. You can do the basic things, the major chemicals and whatever. But if you want to get noble gases or things that are rare or trace, you need to build up your signal. And so the way we're going to do that is we're going to cryo trap everything in this, you know, cold zone of the instrument, and then at apoapse of the orbit, we're going to warm up the cryo trap and analyze it in the mass spectrometer, and hope to make measurements of things like argon 40 and so forth, which will tell us about the degree of connection geologically with the core, with the rock interior of Europa, because it's a decay product of potassium, which is a fairly common element in rocks for the non-geologists out there.
Yeah, so Professor McKinnon, I have a very naive question. So you mentioned, you know, at the very beginning of your talk that there are 3 or 4 moons, right, orbiting around Jupiter.
Mm-hmm.
Yeah, and you mentioned that they all orbit in the same plane. So I just wonder whether this is a coincidence or there's some profound mechanism underlying this.
Yeah, well, you know, I almost put slides in, but as you saw, I already ran over time, so I'm glad I didn't. So, no, we think the same basic process that led to the formation of our solar system, where you have a disk of material, an accretion disk around the sun, creates the planets, and there are lots of complications there. But we think that as Jupiter grows, material flows from the solar nebula onto Jupiter, but because of the conservation of angular momentum, you actually get a disk of material that's rotating around Jupiter. And then the satellites, in some fashion, accrete from the solid materials that are in that cooling disk. And when you look at the sequence of the satellites, you go from rocky Io to Europa, which has a little bit of ice, to Ganymede and Callisto, which are more massive and maybe 60% rock and 40% ice, so both of them. So there's a gradient in composition. They're all in a plane, so it fits in with the Laplace nebular hypothesis of formation. But the fact that they're all in this, 3 of the 4 are in this interesting gravitational resonance is dynamically, it fascinates dynamicists, like people like, you know, like Manoy, but it's also, it's some sort of, as I was mentioning, people who study exoplanet systems, like the various TRAPPIST systems that you might have heard of, many of which have satellites that are believed in mutual resonances. The idea is that there might be some common process. Now, planets forming around stars is not exactly the same as satellites forming around Jupiter, but we shall see. In fact, I recently put together a review article on the formation not of Europa, but of Io, and you can't talk about the formation of Io as a singular body. You have to think about all of the satellites at once, and there must be 10 different models for how these satellites form and where the materials came from and how they were processed. And so we don't have the kind of data we need to rule out most of these, but hopefully in the future. One of the things I'm hoping for from these mass spectrometers, both of these missions, JUICE and Clipper, carry mass spectrometers, is that we will get isotopic data for things like, you know, the D to H, the deuterium to hydrogen ratio, and the 3 flavors of oxygen, oxygen 17, 18, and 16, and the sulfur isotopes. So try to put together a picture of the origin of the satellite system is a background goal for me and certain people. But as I mentioned, the mission got funded, it got accepted by the planetary community and by the United States Congress, which has to fork over the money for these kind of things because of the possibility that Europa has life. I mean, that's the long and short of it. And I have no argument with it. It's fascinating as well. But the Galilean satellites are a fascinating set of bodies. And as I mentioned, we learned a lot from the Galileo mission, but we learned a fraction of what we might have learned if the antenna had not failed on that mission, the main antenna. And we're going to rectify that in about, as I've said, about 8 years. We go into orbit in 8 years if all goes well.
Yeah. Okay, time flies. Yeah.
And I learned that because working on New Horizons, it's not like we sat on our thumbs for 9.5 years. We had things to do, but time did pass.
Yeah, yeah.
And the reward at the end was really worth it.
Yeah, yeah. So yeah, it's quite late in St. Louis. Yeah, we got probably time just for one last question, and it's from Alex Webb. Could you unmute yourself?
Hello. Thanks for a great talk, Bill.
Hi, Alex. How you doing?
Good. Good to see you.
Oh, that's right. I forgot it. So you're in this institution.
Yes. Yeah, this is home base. I had a simple question that I hadn't really considered previously for some reason. EO's overall heat source is pretty well understood. It's not cooling because it's got all this frictional heating from the tidal forcing. How likely is that to play a significant role in the heat budget of the other Galilean moons? Like, do you have a sense of percentages, or have you considered that question? I hadn't previously considered it for some reason.
Europa could be dominated, but obviously it's not active in the way Io is. Io's med heat flow is globally is in watts per meter squared. But I could easily imagine that Europa's heat flow could be greater than that of the Earth, but you'd only have to get above 90 milliwatts per meter squared.
Yeah.
Ganymede, it's in the resonance, but because it's far away and it's given its eccentricity, it actually gets very, very minor amount of heat. So Ganymede and certainly Callisto is just radiogenic, dead in the water practically.
Okay, cool. Thank you.
Let me just mention that there is a question from the chat, which I'll just very directly respond to.
One question from the chat, yeah.
Yiki Kyan. Bill, any direct radar observation of Europa to prove the ocean yet, like those from Arecibo? No. No, the radar, the longest radar wavelength that you could imagine sending from the Earth would be, let's say, from now, because Arecibo, as you know, collapsed, would be right now from the VLA in New Mexico, and it would be 70 centimeters. And so that's you can bounce that off the surface. Maybe you could receive it in the from the Chinese radio telescope. If we actually could work together, that would be great. But that you wouldn't be able to get down to the depth necessary. So as I say, we are carrying radar systems there that have wavelengths not in 70 centimeters, but 33 meters in vacuum. And you need that because subsurface scattering will take the energy out of the radar beam. There's some people think that the radar is going to be compromised, but I suspect from our observations of Mars that we will be able to see kilometers into the surface. At least that's my hope.
Okay, so thank you again. Thank you again for this very exciting talk and for all the inspiring discussions afterwards. And we hope that we will have the pleasure to invite you again, probably to come here in person.
I would love to visit.
Traveling is more convenient. Yeah. Okay. So thank you very much. Yeah. Have a good night. Yeah.
And good morning to everyone. Thank you. Thank you again.
Yeah. Take care. Bye.
Bye.
Thanks, Bill.